All right, so good day, one and all. This is a tutorial video on basic medical chemistry taught by Dr. Abner Broby. This video will focus on alkyl halides, right? Good. Now, this is an initiative by Samuel Tampanga Wepia, aspiring for HESA president next semester. Good. So, I think we have heard more of the words, I'll do this, I'll do that. Yeah. So then I decided to do something very different. That is action, right? Good. So this is a sample video of one of the initiatives I want to bring on board when I'm voted into power as the HESA president. Now, let me sound this caution. This is an academic material and should be used irrespective of your political affiliation, right? Good. So you should still use it, whether you are voting for Samuel Tampanga Wepia or not. Good. So the content, alkyl halides. Now, these are our references, yes, for further reading. So what do we have to talk about with regards to alkyl halides? We have to talk about the introduction, nomenclature, synthesis, properties, reactions, commercial and pharmaceutical significance. I think this is why we are learning the topic. Good. So alkyl halides. Now, as the name implies, we have two words here, alkyl, right? And then halide. So alkyl from alkenes, right? So if an alkene loses a hydrogen, it becomes an alkyl group, right? Very simple. And then the halide here is from halogen. It's from halogen, right? Now, halogen is group 7 of the periodic table, right? Now, if a halogen forms a compound, we call it a halide. Very simple, right? Good. So we are saying that they are compounds with halogen substituents, right? Now, if the fluorine is a substituent, it's fluoro, fluorine becomes chloro, bromine becomes bromo, iodine becomes iodo, right? Bonded to an alkyl group. So we've seen the two parts, a compound with an alkyl group and a halogen substitute, right? Now the general formula for alkyl halide is Rx. So the R is the alkyl group, the X is the halogen. The halogens are fluorine, chlorine, bromine, and iodine. Now examples of alkyl halide, we have ethyl bromide. Ethyl bromide is a common name. The IUPAC name is bromoethane, right? We have chloroform, we have other solvents here, right? 1,1,1 trichloroethane, halothane. Good. Now we are saying that the halogen derivatives of alkenes are called alkyl halides, of alkenes are called alkynyl halides, of alkynes are called alkynyl halides, right? So alkynyl halides, sorry, then arenes are called aryl halides. Good. Now, this is the general formula for an alkyl group, right? It's actually R. So you see the CC here. Any hydrocarbon that has lost the hydrogen becomes an alkyl group. Now, these are the halogens as arranged on the periodic table. We have fluorine, chlorine, bromine, and iodine, right? Good. Classifications of alkyl halides. Now, alkyl halides can be classified into primary, secondary, and tertiary, depending on the number of carbons directly bonded to the carbon bearing the halogen. Very simple, right? So assuming this is the carbon bearing the halogen X, right? Now, if this carbon is bonded to only one other carbon, carbon form 4 bonds. So if this one is bonded to one carbon, it means the other bonds are hydrogens, right? We call this a primary alkyl halide. Now, if the carbon bonded to the halogen has 2 other carbons directly attached to it, that means the last one will be a hydrogen, right? We'll call this a secondary alkyl halide. Now, if the carbon bonded directly to the halogen is bonded to 3 other carbons, right? 3 other carbons, then we call it what? A tertiary alkyl halide. A tertiary alkyl halide. Now, if it happens that the carbon here is bonded to no other carbon, that is bonded to only hydrogens, then we have a methyl halide, Very simple. Good. Now we have an exercise to classify the following into primary, secondary, tertiary and methyl halides. Now, how can we do that? We can do that by looking at the structure. If you are very good in chemistry, like by looking at this, you should know it's primary, right? It's primary. Good. But then if you can't, then you have to draw out the structure. So let's draw it out. We can draw around just the carbon directly attached to the chlorine, which is the halogen, so that we can see. So the carbon here is bonded to another carbon at the back, which is bonded to hydrogen, and then the two methyl group CH3, CH3. Now this carbon here is bonded to chlorine, is bonded to two hydrogens, H and H. Right. Now, because this carbon is bonded to only one other carbon, it is primary. Let's draw the second one. So carbon bonded to Br. There are 3 CH groups around it. 3 CH3 groups around it. Right. Good. Now, this carbon is bonded to 3 other carbons and it's a tertiary. Tertiary. Now, this is the carbon in question. This carbon is the carbon in question. This carbon has one carbon at the back, right? It has Cl. It has one hydrogen here. It has another hydrogen. It has two hydrogens directly bonded to it, right? Now, because it has only one other carbon directly attached to it, it is primary. Good. Now, if I come here, the carbon in question is this one. This carbon is directly bonded to this carbon, also bonded to this carbon and this hydrogen. Now, because it has two other carbons bonded to it, it is secondary, right? Now, the last question, this is the carbon in question, right? It is bonded to this carbon, also bonded to this carbon. And then you realize that it's bonded to just two other carbons, which is secondary. The third bond is a hydrogen that we don't show in skeletal structure, right? Good. Now, carbon, halogen, bond length, and bond strength. Now, I have to see one general thing here before I explain this slide. The general thing here is that the longer the bond, the weaker the bond. So longer, weaker. So then if you realize that the bond length is very long, then we are thinking the strength is what? Very weak, it's low, right? Now, if you have a shorter bond, right? A shorter bond is a stronger bond. So then we have to use these two principles. Now, what happens? We are talking about the carbon halogen bond, right? Now, the carbon will have the same atomic size, right? Because it's carbon in any other instance. But then the different halogens coming in would have different sizes. Now, if you are reminiscing, then we can think about our normal inorganic chemistry in SHS. Now, they told us that down the group, the size of the atom increases, such that fluorine will have the smallest size, going towards chlorine, then bromine, and then finally iodine. So the size increases. So then if I'm forming a bond between carbon, carbon would roughly have the same size, right? And then there's an overlap to form the sigma bond. Now this can be fluorine. Chlorine will be bigger than fluorine, so something like this. Bromine would also be bigger, something like this. And then iodine will also be bigger than something like this. Now I realize that the internuclear distance here increases. The length in this bond increases, right? So this is not the chemistry, right? Because that's not how actually electrons behave. But then this is just to explain to us what is happening. So now the carbon sizes are equal, but then down the group, what do we observe? We observe that the size of the halogen is increasing, right? That is making the bond length increase. Now, once the bond length is increasing, the bond strength is what's becoming weaker. And so we are saying that as you go down from F to Cl to Br to I, the bond length increases, right? Now, because the bond length increases, the bond strength what? Decreases. And so the CF, the F has the smallest size, and then it will have the shortest bond length, and you have the strongest bond. Now, we are saying that because fluoroalkenes have the strongest bond, right? Because they are the shortest, they are highly resistant to bond breaking under most conditions. So they are least reactive. Now we are introducing a new term that the stronger your bond, the less reactive you are. Because when you are forming the bond, you have to first break, or when you are reacting, you have to first break the bond, right? The bond between the carbon and the halogen has to be broken, right? Good. So then we can see that per that analogy, then this one will be the least reactive because the bond is the strongest, right? Followed by this one, and then this one, and then the Ci will be the most reactive because it has the weakest bond. Are we following? So this is the order explained to us in the next slide, right? That is it here. That in terms of reactivity, the most reactive is Hi and the least reactive is what? The Hf. Good. Now, nomenclature. I'll read the general rules here, but then we'll use specific examples to explain the nomenclature. So then we are saying that they are named as haloalkene. That is, the halogen becomes the substituent and the alkene becomes the parent name, right? Then we are saying that treating the haloalkenes as substituent and then the alkenes as a parent chain. The haloalkenes, fluorochlorobromoiodoalkene. The longest alkyl chain is considered as the parent. The carbon chain is numbered in the direction that gives the substituent carbon the lowest number for different halogens. Now, assign each substituent a number according to its position on the chain, number all and list them in alphabetical order. If the parent chain can be properly numbered from either end by step 2, begin at the end nearer to the substituent that has alphabetical order, right? Good. So we are saying that these are the rules that you have to follow, right? But then I'll use specific example to explain, as I said. So let's go to the first one. Now I can name I can number my carbons from here 1, 2, 3, 4, 5, right? Good. But then if I do that, the fluorine is on this C and then it will be given 5. One of the rules told us that we have to give the least number to the substituent. And so appropriately, we have to number from this end as it has been shown here. 1, 2, 3, 4, 5, right? Good. Now, the name becomes 1-fluoropentene, right? Good. Now, the next one, 1, 2, 3, 4, 5, right? We can also number from here. If you try numbering from here, 1, 2, 3, 4, 5. Now, what happens is that your methane will be on the second position, the chlorine will be on the third position, then the bromine will be on the fifth position. The current numbering will put bromine on the first position, chlorine on the third position, and then the methyl group on the fourth position. If I sum these numbers, I'm getting 8. If I sum these numbers, I'm getting 10. So then we have to choose the one that gives us the least sum, right? So we number it as it has been shown in the slide. Good. So after numbering, then we name it in alphabetical order. We name it in alphabetical order. So we have 1 bromo, 3 chloro, 4 methyl. The longest chain is 5 carbon chain, right? Pentane. The next one. So we've numbered it accurately from 1, 2, 3, 4, 5, 6. Now you could have also numbered it 1, 2, 3, 4, 5, 6. The numbering would have been 2, 5, just as this one is. But then we are seeing that if it happens like this, choose the one that obeys alphabetical order. So we number such that because we know the B comes before the C in the normal alphabetical order, the B will be numbered before the C, right? That is the argument we are putting across here. Good. So then the name will be 2-bromo, 5-methyl hexane. Now we are supposed to try these ones. Let me give out the name. And so then we number 1, 2, 3, 4. This will be 1-iodo butane. Then next one, 1, 2, 3, 4. So then I will have 1-chloro, 3-methyl butane. Right. Good. The next one. Now I can number from here or from here, but then you realize that I have to number such that I'll give the one that obeys alphabetical order the priority. So I'll have 1, 2, 3, 4, 5, 6. So then it will be 2-bromo, 5-chlorohexene. Very simple, right? Good. Then the next one. So then the numbering can be done in different ways, but you have to number so that the naming becomes very easy. So then I'll number it from here. 1, 2, 3, 4, 5. So I would have 1-chloro, 1-chloro, 3-ethyl. So 1-chloro, 3-ethyl, 4-iodo, pentane. Very simple. Good. So you realize I'm also thinking through what I was doing. I'm not sure the answers. We don't choose chemistry answers, right? We just understand and then follow suit. Good. Now the last one here. 1, 2, 3, 4, 5. Now you can also number from this other end, but then if you number, you realize that the sum of the numbers of the subsequent will be too big for you, right? So you maintain this one. Good. So I would have 1 bromo. So 1 bromo. Oh, sorry. So the bromines are 2. So then I will have 1,5-dibromo, 1,5-dibromo, 2,2-dimethyl, 2,2-dimethyl pentane. Very simple. Very simple. Now you realize that between two numbers, I put a comma. Between a number and a letter, there's a dash, right? Very simple. Good. So the answers are here. You can confirm the answers. Now we are supposed to draw structures corresponding to this name. Always, what will make your life very easy is that you start from the parent name. So hexane, 6 carbons, 1, 2, 3, 4, 5, 6, right? Then 4-methyl. So on the fourth carbon, 1, 2, 3, 4. There's a methyl group here, right? Now 2,3-dichloro. So on position 2, there's a chlorine group. On position 3, there's a chlorine group. Now carbon form 4 bonds, so let's give each carbon 4 bonds. Now where there are no substituents already, what do? We add a hydrogen. So I'll have hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen, 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 hydrogen here, hydrogen here, and hydrogen here. That will be my compound, right? Good. Now, the next one, let's try the skeletal structure. So it will still be hexane, right? So, okay. So this will be it. Now, each vertex here would be a carbon. So 1, 2, 3, 4, 5, 6, right? 6 carbons. Now, we have 3,3-dimethyl. So 1, 2, 3. 1 methyl group here, another methyl group here, right? Then chloro, 2 chloro. So on the second carbon, I'll put a C out there, and this will be my structure. Very simple. Now, if you understand the skeletal structure, it's very simple. If you don't understand it, you don't stress, right? Good. Now, let me use the same skeletal structure for the next one because I feel this one is very easy. Sometimes the skeletal structure, which is quite challenging. So hexane, right? 2, 3, 4, 5, 6. Good. Then I have 2-methyl. So a methyl group. Then 4-ethyl. So 1, 2, 3, 4. Ethyl group, right? Then ethyl group is 2 carbons. Then I have bromo. So Br, right? Good. Then I'm done. So very simple. The last one, pentene. 2, 3, 4, 5. Good. So this is pentene. 3-ethyl. So 1, 2, 3. So ethyl group, right? And then 3-bromo. So there's a Br here. Very simple. Good. So these are the answers. You can verify the answers. Common names. So I think it's more usual for you to hear people calling compounds by their common name than their IUPAC name because some of the IUPAC names are complicated. So it is very important to take note of common names. And then from the knowledge we have about Dr. Abna Broby, in exams, she will give you a common name. So of giving you the IUPAC name, because we can easily deduce structure from IUPAC name, we usually give common names. Now, common names are useful only for small alkyl groups. Very important. The alkyl groups is treated as a substituent on the halide. So the ideal thing is that we treat the halogen as a substituent on the alkyl group, right? Now we are not treating the halogen as a substituent. We are actually treating the alkyl group as a substituent on the halide. So this is methyl fluoride instead of fluoromethane. This is pentyl chloride instead of chloropentane. This is cyclohexyl iodide. So the names, the parents' names are now the halogens. Good. Now, other common names. So ethyl fluoride and butyl chloride, isopropyl bromide. These are all common names that we can keep. More common names for solvents. Now, we are saying that CH2X2 is called methylene halide. Makes sense because this CH2 group is called a methylene group. CH2 is called a methylene group. So if you have CH2, Cl2, then I have a methylene chloride, right? Now, if you have any compound in this form, CHX3, where X is a halogen, then we call it a haloform, right? Haloform. So then if the halogen is chlorine, then we have chloroform. We have other compounds like iodoform, right? Good. Then CX4 is carbon tetrahalide. So if it's chlorine, then we have carbon tetrachloride. Very simple. Good. Physical properties of alkyl halides. Good. So the first physical property is the boiling point. Now, the boiling point, let me make it very clear here, depends on the intermolecular bonding. Intermolecular bonding. And so the first thing we have to ask ourselves is that what type of intermolecular bonding exists in alkyl halides? Now, the answer is the van der Waals force. So we have the van der Waals force between alkyl halides, right? Good. Now, the van der Waals force can be explained, depending on your reference, into two forms. We have the induced dipole, right? And the dipole. Now, the fluorine, the halogens have some level of electronegativity, so induce some level of polarity. Even though it doesn't make the compound too polar, there's some level of what? Polarity, right? Good. So the polar nature here contributes to strengthening the bonding in alkyl halides relative to the normal alkenes, right? Because it is quite polar, it has some charges to interact. Now, if you consider this bond is a polar bond, so the fluorine here, because the fluorine is more electronegative than the carbon, the bond shared, the electron shared between the carbon and the fluorine shift a little bit to the fluorine, such that the fluorine will assume a partial negative charge and the carbon will assume a partial positive charge, right? Good. And so it is polar. And this polarity can help the molecules to arrange well and bond more, right? And that will raise the boiling point relative to the normal alkenes, which are non-polar, right? Good, that's the first thing. The next thing is the molecular weight. The molecular weight. Now, for van der Waals force, the higher the molecular weight, the higher the extent of bonding between the molecules, right? And so we are seeing that alkyl halides have higher boiling points than alkenes of the same number of carbon because of greater molecular weight and it's more polar. Now, why would they have greater molecular weight if we are talking about the same number of carbons? Now, assuming I have propane, the alkyl halide derivative, if I'm bringing chlorine, will be me removing one hydrogen here, so the CH will be 2, and then adding the chlorine. Now, hydrogen is lighter than chlorine, so if I bring chlorine, this new compound, the propyl chloride, will be heavier than the propane because I took something light and I brought something heavier, right? Now, because of the increased molecular weight, it will have a higher van der Waals bonding, that's intermolecular bonding. and then give it a higher boiling point than normal alkenes, right? Good. So that is it. I think this table is very consistent with what we are talking about. And the next thing that we have to also take note of is that for isomeric halides, boiling point decreases with increasing branching. There's another property that we didn't mention here that is worth mentioning, that van der Waals force is favored by surface area, such that the bigger your surface area, the higher your extent of intermolecular bonding and the higher your boiling point, right? Good. And so if I have a structure which is branched like this, right? This is tet butyl chloride, right? And then tet butyl chloride has 4 carbons. I can also have, right? This is the N-butyl chloride. Now, this N-butyl chloride has a larger surface area compared to the tet-butyl chloride. Hence, this N-butyl chloride will have a higher boiling point. That's what we are seeing, right? And so if the branching increases, what happens is that it decreases the surface area, reducing the extent of bonding between the molecules, right? And then once the extent of bonding between the molecules decreases, what happens? The boiling point decreases. So very simple. This is N-butyl chloride, and then we have other substituents like that. This is, so they are branchings, right? Now this is the tet-butyl that I do, and then it would have the lowest boiling point. So as branching increases, the boiling point decreases. The next physical property is solubility. Now we are seeing that although alkyl halides are polar, they are not sufficiently polar, or they don't have polar hydrogens. That's the key thing. They don't have polar hydrogens to form hydrogen bond with what? With water. So they are not soluble. So alkyl halides are quite polar, but then they are insoluble in water because they cannot form hydrogen bond with water. Very simple. But then they are soluble in what? In organic solvents. They are soluble in organic solvents. Now, there's a note here saying that many fluoroalkenes, including methylene chloride, chloroform, and carbon tetrachloride, have cumulative toxicity and are carcinogenic. This is more stressed in pharmacology, especially this one. You realize how earth-forming free radical can actually lead to some carcinogenic activities in your body. The density. Now we are saying that alkyl fluorides and chlorides are less dense than water. However, alkyl bromides and iodides are more dense than water. Very simple, right? So you keep this one. But then there's something else that you have to take note of. That is alkyl fluorides and alkyl chlorides. Those with just one chlorine atom are less dense. That means the general statement here is for the one that are monofluorinated or monochlorinated, right? Now, if any alkyl chloride has 2 or more chlorine atoms, it is denser than water. So then it means this is not always true. We should also read this. But then irrespective, whether it's monobromination or mono iodation, that's if it's a thing, right? It is still more dense than water. Good. Now, we are supposed to compare this. We have talked about them already, so very simple. Now, we are supposed to arrange this in order of increasing boiling point. You realize that the number of carbon and hydrogens here are the same. So the difference coming in is what? Is because of the halogens, right? Now, the halogens, one key thing that would differentiate is the molecular weight, right? We said the higher the molecular weight, the higher the boiling point. So then we can just use their molecular weight. Iodine is the heaviest, followed by bromine, and then the least will be what? Will be fluorine. Because we are supposed to arrange in increasing, it is supposed to be from the smallest to the biggest. So the first one should be fluorine, followed by bromine, and then iodine. And the next question is saying, why are alkyl halides insoluble in water? Now, if you are insoluble in water, it means you cannot form hydrogen bonds with water. That is the reason, right? It can't form hydrogen bonds with water, right? Yes, and then because it's slightly non-polar, it can dissolve in what? Organic solvent. Very simple. Good. Now, synthesis of alkyl halides. So we have halogenation of alkane with chlorine gas or bromine gas in the presence of UV radiation. Now, this is the free radical reaction. I think it will be taught in alkenes, right? And then it was also taught in SHS. This slide will not focus on that, right? Now, we can also synthesize alkyl halides from alcohol, right, with HX, PX3. That is where X is iodine, bromine, or chlorine, or we can use thionyl chloride. Now, this is the major synthetic pathway. If you want to synthesize alkyl halide, this is the major method. And then, because of that, the slide will focus on this one. Now, we can also add HX to alkene, and then this addition reaction can result in forming alkyl halides, right? We can also add X2, that's bromine liquid or chlorine gas to alkene to get a vicinal dihalide. So vicinal dihalide means that we have the bromine substituted on two adjacent carbon atom. There's another one called geminal. Geminal will have the halogens substituted on the same carbon atom, right? So vicinal is when we have the halogens on two adjacent carbon atoms. Good. So let's talk about the major synthetic pathway for preparation of alkyl halides. Now we are seeing that we prepare them from alcohols, right? Good. Alcohols react with a variety of reagents to yield alkyl halides. The first one, alcohols react with hydrogen halide, that's HCl, HBr, and HI to give alkyl halide. So this is the overall reaction stated. Now we have the alcohol, the hydroxyl group of the alcohol will be removed and then the halogen will be replaced, right? Now, the hydroxyl group will go and form water as a byproduct. Very simple. You're seeing that this reaction of an alcohol with a hydrogen halide is a substitution reaction. A halogen, usually chlorine or bromine, replaces the hydroxyl group as a substituent on the carbon. Among the various classes of alcohol, tertiary alcohols are observed to be most reactive and primary least reactive. Now, we'll explain this as we go on. The reason why we have tertiary being most reactive for this method and then the primary being least reactive, right? So we are saying that if, okay, and then there's even a fact here that if there's methyl, that's methanol, right? If there's methyl alcohol, the methyl alcohol is actually less reactive than the primary. So let's start from the methyl alcohol before we get to the general primary alcohol, secondary, and then tertiary alcohols. So then there's an actual example where we have a tert butyl alcohol reacting with HCl to form our tert butyl chloride and water. Now we are seeing this an SN1 reaction and then involves the formation of a carbocation. Let me share my screen and explain the mechanism of action here. So then we have a tert butyl. So CH3, 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 right? And then OH plus HCl reacting to form. So this is the general formula, right? Good. Now I want to show the mechanism. So then usually what happens? What happens is that the HCl will dissociate, right? So the HCl will dissociate in water to give me H3O plus Cl minus. So this is the first thing that will happen, right? Good. Now, once this thing happens, it means I have this in water. Then what will happen is that this is the structure of the hydrozonium ion. Now, because oxygen has formed 3 bonds, or because oxygen has donated its lone pair to the proton from the H plus here, that's why it has a plus on it. Good. So the oxygen, the lone pairs on this oxygen will attract this hydrogen. The bond here will break onto the oxygen here. Now, what will I form? I'll form CH3. So these sides will not change, right? OH2 plus, right? Then the oxygen here has formed an extra bond by donating its lone pair, right? This bond has broken onto this, so I'll form molecule of water here. When this breaks, the plus neutralizes, then I'll form water. This is what I have. Now, the water group formed here, we see it is what? A good living group. So what it will do is that it will break onto this to neutralize it. Now I would form water as a byproduct again from this side, right? And then I'll form a carbocation. Carbocation because the plus sign is on the carbon. That is what we call a carbocation, right? Now this carbocation is quite stable. It's quite stable. Let me just explain what will happen later. Now with a C or minus, right? Because there's positive charge here, the minus will attack this positive charge. So that will lead to me forming my final product, C3. So that is how I form my butyl chloride. Very simple. So I was explaining why the formation of this one is favored. Now, always, because this procedure or this method follows the SN1 reaction, it involves forming a carbocation, right? Now, the carbocation is ideally unstable, right? And then the stable ones have lesser positive on them. The nature of the methyl groups here on the carbon is that they are electron donating. The methyl groups are electron donating. So what it does is that it can shift some of the electrons through inductive effect to this carbon. It can shift. So all these three groups are shifting their electrons towards this carbon. Now what would they do? It will decrease the extent of positive here, right? And make this carbocation intermediate stable. Now, because it's stable, it can form a little bit. If we are talking about a secondary alcohol, it means we don't have any methyl group here. We have just two methyl groups. So the methyl groups are trying to stabilize. This one is given the carbocation electrons through inductive effect. This is also given through inductive effect. But then the reduction of the positive charge will not be as much as it was in the tertiary. Now, if it's primary, it means we have only one carbon directly attached to this carbon, right? That means the sharing of the electron or the shifting of the electron is done by only one alkyl group. And then that is not enough to reduce the extent of positive. Because that intermediate carbocation is highly unstable, it will not form. Because reactions proceed to form more stable products. And then if you are not stable, you wouldn't form. No person or no reagent would like to form a more unstable product, right? Unless it is forced by conditions. On a normal day, we all want to spontaneously go into stability. And so because the primary carbocation is least stable, it wouldn't form. Because the secondary is somehow stable, sometimes it can form, but then the one that forms appreciably is the tertiary carbocation because it has three methyl groups that will donate electrons to the carbocation by inductive effect. Very simple. Very simple. So that's the concept. That is why tertiary forms most. Let's go back to the slide and then continue. So back to the slide. Now, the method has been explained here. You realize that the slow step here is what? Is when we are forming the carbocation. And then the slowest step in a series of steps is what we call the rate determinant step. Right? So this one determines the overall reaction. And then if the carbocation you are forming here is not stable, the reaction will not proceed to give you appreciable product. These are the other methods. The thionyl chloride. The thionyl chloride plus the alcohol gives you alkyl chloride and then gives you sulfur dioxide and HCl as side product. Then we have reaction with phosphorus halide, right? Good. So the halides that can be used in this reaction here is Cl and then bromine. The side product that you form is phosphoric acid. Phosphoric acid. Good. Now properties. So we are talking about the property of the carbon halogen bond. I've already explained this, so let's go through it. Now the carbon halogen bond of alkyl halide is polarized. So this is it. First thing, it is polarized. Carbon and then the halogen. polarized, right? Now, the polarized here, it is polarized, meaning that it has poles. The poles here is the positive and then the negative poles, right? The poles we are talking about are charges. Now, the charges will result because of difference in electronegativity. So if any compound, any bond has is polar or has polarity, it is because of a difference in electronegativity of the atoms involved in that bond, right? Now we are saying that the halogen is more electronegative than carbon. So what happens is that because the halogen is more electronegative, electronegativity is your ability to put shared paired electrons towards yourself in a bond. So now they are sharing this electron, right? Because the halogen is more electronegative, it can shift the electron towards itself. When it shifts the electron towards itself, it becomes partially negative as if it was gaining the electron as an anion. And then carbon becomes partially positive as if it was losing the electron, as in the case of a cation, right? So that's what we are talking about. So carbon bears a partial positive, halogen bears a partial negative, right? Now, because the carbon is a partial positive, it can be attacked by nucleophile. Nucleophile. Now, this is introducing us to the reactivity of alkyl halides. The first thing we said is that now the carbon and the halogen bond is polarized. Polarized because they have difference in electronegativity. And then the electronegativity of the halogen is higher than that of the carbon, making the carbon partially positive. Because it's partially positive, it can be attacked by a nucleophile, right? Now, what is a nucleophile? From basic term, nucleo is the nucleus. The nucleus from basic chemistry is made of the protons and neutrons. The neutrons are neutrally charged. They have no charge, right? The protons are positively charged. So basically, the nucleus is positively charged. So if you talk about nucleo, you are talking about positive charge. File is love, as English, right? So if you say a species is a nucleophile, it means it loves positive charge. Now, why would you love positive charge? In basic physics, unlike poles attract. So the fact that you love positive charge will imply that you are negatively charged, which is true in this case. So nucleophiles are negatively charged. Now, what makes them negatively charged are electrons. So then we say that nucleophiles are electron-rich species that will attack a positive charge or electrophile, right? So very simple. Good. Now, we are saying that because this is partially positive, it can be attacked by a nucleophile. That is any electron-rich species. Because it's positive, it can be attacked by any negative species. That is what we are saying, right? There's another term called electrophile. Electrophile means you love electrons. And then because before you love electrons, electrons are negatively charged. You should be positive charged. So then electrophiles are positively charged. They lack electrons, therefore they love electrons. The definitions are in this slide. So we can go through the definition. Now we have been introduced the reactions. We should take note that what will attack the carbon bearing the halogen is a nucleophile. So throughout this reaction, we'll be mentioning nucleophiles, knowing very well that nucleophiles will attack the carbon bearing the chlorine or the halogen. And then in other instances, I'll call it the alpha carbon. So if I see alpha carbon, there's a carbon bearing the halogen. Okay. So we are saying that alkyl halide undergo two types of reaction: substitution reaction and elimination reaction. In substitution reaction, the S group in the RX is replaced by a different group, right? So substitution is a replacement reaction. So one group will come and substitute the other group. And then in this case, the S group here is being replaced by the OH group, right? Now there's another reaction called the elimination reaction. Now, elimination reaction will lead to the formation of unsaturation. Unsaturation in basic terms is double bond or triple bond. That is unsaturation. So elimination reaction will proceed to form unsaturation. Now, the particular type of elimination reaction that happens when we are talking about alkyl halide is dehydrohalogenation. That is, we removing a halogen and removing a hydrogen to form the unsaturation. Chemistry is nice. Good. So then, nucleophilic substitution reaction. We first of all said that it will be attacked by a nucleophile, so nucleophilic. Then substitution means the nucleophile is replacing something else, right? Good. So then we are saying that nucleophilic substitution is a versatile reaction widely used in organic synthesis. The general reaction is Rx plus the nucleophile. So the nucleophile will replace the and then displace the X. Now there are two possible ionic mechanisms for nucleophilic substitution. We have the SN1 mechanism and SN2 mechanism. The S is for substitution, the N is for nucleophilic. The one is for unimolecular, because the rate determining step involves only one molecule. We realize that as we go along. The two is for bimolecular, because the rate determining step, which is the slowest step, involves two molecules, right? Now we are saying that in both SN1 and SN2 reaction, the mechanism involves the loss of a halogen anion from the Rx. Now, in these two reactions, we lose a halogen. The halogens are called leaving groups. Generally, we know halogens like chlorine and bromine to be good leaving groups. So they leave and they abstract the electrons that was shared with the carbon, leaving a positive charge on the carbon, right? Yes. So we'll talk about that more. Right, so this is the leaving group. The halogens are called leaving groups. They take the electrons here away, leaving a positive charge on the alkyl group, and then going with negative charge. Because the positive charge is on a carbon, we call it a carbocation, right? Good. Now, this is a slow step, is the redetermining step, right? And then it involves one species if we are talking about the SN1. So this SN1, you realize that it was just one species. It left the species, the halogen broke on its own and then formed the carbocation. This is the redetermining step, right? And then you realize that it involves just one species, just one reactant. So then we are saying it's a unimolecular substitution reaction. Good. Now, after the carbocation is formed, it is attacked by the nucleophile. This is a very fast reaction, right? Very fast. So it's not really determinate. Good. Now I realize that if you want to determine the overall speed of the reaction, it would just be dependent on the one that was slow, which is the Rx reactant. Good. So the rate of the reaction, that's how fast the reaction proceeds, depends on just one reactant. That is why we say it is what? It is nucleophile. That's why we say it is unimolecular. Sorry, that's why we say it is unimolecular. Now we are explaining that this is very reactive. The carbocation is very reactive. Now you realize that carbon is supposed to have 8 electrons around it. Now, when it loses this bond and then it becomes something like this, what has happened is that it has 6 electrons instead of what the 8 electrons that's supposed to have, and that makes it very reactive. And so when the nucleophile is attacking, it's very easy, very simple, and then it does not determine the rate of reaction. Very simple. Now we are saying that the most important feature of the SN1 reaction is the formation of the carbocation intermediate, right? Now, the more stable carbocation is favored. I've explained that already. Good. Now, the carbocation can be classified as primary, secondary, and tertiary, depending on the number of carbon atoms attached to it. Now, we have a methyl here, the methyl. Good. Now, methyl will have no carbon attached to it, right? If it's primary, it has 1 carbon attached to it. Secondary has 2 carbons. Tertiary has 3 carbons attached to it. And I said the alkyl groups are electron donating through inductive effect, right? But because of this character, they can reduce the extent of positive and then make the cation more stable, right? So we are saying that the most favored will be the tertiary. Secondary alkyl halide forms secondary carbocation. That's fairly stable and may undergo SN1 reaction, but primary is unstable, right? Primary carbocation is unstable. So primary alkyl halide will not undergo SN1 reaction. Let's take note of that. But primary alkyl halides will not undergo SN1 reactions. So substitution reaction of primary alkyl halide proceeds by SN2. If you are talking about substitution reaction with primary alkyl halide, then we are thinking of SN2 reactions, right? Good. So we are saying that when we start with any material, right, and then it is chiral. When we are done with the substitution reaction, there's a formation of a racemic mixture. That is 50-50 or 50 to 50% mixture of R and S enantiomer, right? So there will be half of the product will be R, half of the product will be S. Very simple. Good. Identify the compound in the pair below that reacts at the faster rate in SN1 reaction. So we are supposed to compare the reaction rate in SN1 reaction. Now, before we attempt this question, we should know that if it's tertiary, it is formed well. If it's secondary, it is fairly formed. And then if it happens that it's the primary, then it wouldn't form, right? So we should draw the structure. These are the structures. This is isopropyl bromide and isobutyl bromide. Now, this is the carbon of focus when we come to this place. And then this carbon is bonded to two other carbons. So it is secondary. Okay. Now, this is the carbon of focus. This carbon is directly bonded to only one other carbon. So it is primary. Now, from our basic chemistry, it means that if I lose this bromine in SN1, the plus will come here. I'll form a secondary carbocation. This will form a primary carbocation. Because primary carbocations are highly unstable, it will not form. So this one will be faster than this. Very simple. So we can read the English here. Good. Now, bimolecular SN2 reaction. So the same overall reaction, right? But then the molecular mechanism changes a little bit. Good. So in this case, we do not form a carbocation intermediate. So let me just read so we can go. We are saying that the rate of the reaction entails two species. That's why we call it bimolecular. That is the reactant and the nucleophile. The nucleophile forms a new bond to the carbon at the same time as the bond of the halogen atom is broken. So as we are forming a bond with a carbon, that's the alpha carbon, then the halogen is also breaking. So the intermediate will be a pentacoordinate compound, right? Let's use this figure to illustrate now. So this is the nucleophile attacking this carbon, right? The carbon bearing the partial positive. Now you realize that as this is attacking, right? As the nucleophile is attacking, the I is also breaking away. And so the intermediate or the transition state is formed where we have a pentacoordinate intermediate. So it's like the carbon is forming 5 bonds, right? Now there's a partially formed nucleophile bond and there's a partially broken halogen here, right? And then in the final product, we'll have it fully broken and then this one fully formed. So you realize that there's no carbocation intermediate here. There is no carbocation intermediate here. And that is SN2 reaction. You realize that the rate of the reaction is when we are moving from here to here, and then it depends on both reactants. So we are saying that it's bimolecular or bimolecular. Very simple. So we are saying that one thing we should take note of here is that because we are forming a pentacoordinate carbon, steric hindrance is something which really affects the mechanism. Now, if the carbon which bears the halogen has bulky groups around it, if it has bulky group around it, what happens is that there's spatial hindrance. There's no space, right, for the new nucleophile to come and then attack. And so if there's steric hindrance, the mechanism cannot happen, or you cannot undergo SN2 reaction. So if you consider the alkyl halides from primary, secondary, and tertiary, let's consider them. Now, this is carbon. So if it's primary, the hydrogens are, okay. So let me make it, if it's a methyl group, right? If it's a methyl group, the hydrogens are very small in size, and then they are around. So there's a lot of space for the nucleophile to attack. Now, if it's primary, you realize that there will be some hindrance coming in small. It's primary, right? So some hindrance coming in from small. So the carbon is quite bulky. Now, it gets worse if it becomes secondary, because the bulkiness will increase because the carbon is bigger than the hydrogen. If I take this last hydrogen and add another carbon, then I've increased the steric hindrance appreciably, right? Now we are saying that tertiary will be least favored in SN2 reaction because of this spatial hindrance. There are too many carbons here and there's no space for the nucleophile to attack. Very simple. So if we talk about SN2 reactions, the most favored is methyl followed by primary. Then the least favored is what? The tertiary, opposite of SN1. Now, the rate is dependent on the concentration of the two species. The higher the concentration, it will increase the molecular collision and increase the rate of reaction. That's what we are talking about, right? So then I've already explained this, that the nucleophile approach the carbon halogen bond at 180 degrees, and bulky group will prevent the nucleophile from approaching the central atom, right? And then this will be the general order. I've already explained that in the previous slide. Good. So then this will be a table trying to show us the relative rates. That's how fast the reaction will occur if we are dealing with primary, secondary, tertiary. Tertiary. If we are talking about SN2 reactions, SN2 reactions. So the general standard here is this secondary. That is the relative rate is 1. Now, if it's 1, it means if we are talking about 10, it's 10 over 10, right? So this is the standard. So we are comparing everything to this one, this compound, right? This compound is secondary. Now, if you compare it to the methyl bromide is over 1,000 times faster. If it's primary, it's like 50 times faster. If it's tertiary, it is 0.01 times faster, right? Or we can say slow. It's actually slower. So it is even less than this. So it is very slow. So we realize that tertiary will be least favored, right? Now, between the primary, we can also compare because this is primary, this is primary, this is primary, this is primary. So what has happened? Now, this one has straight chain, it's primary. Then the next primary has the same, it's a longer chain, right? Now, it means that as the chain length increases, the bulkiness increases and the rate for SN2 decreases, right? Good. Now, if you consider these two, they have the same number of carbon atom, but then the branching has increased. Now, once we increase branching, right, it means you are increasing how compact the structure is, and then the steric hindrance around the alpha carbon that we are interested in. And so the rate will also decrease. That is why it decreased from 20 to 2, right? Good. And then this is a tet. This is a new pentyl. New pentyl. Now, new pentyl will have a lot of branching. This is the structure of new pentyl, right? So because it's also primary anyways, but because of this bulky structure here, the rate will also decrease. So it's primary, but because of branching. So what we have to keep in mind that branching will increase the steric hindrance and then will decrease the rate in SN2 reaction. Very simple. Very simple. So then we've talked about all these. We should read through them. Yes. Now the chirality. So we are saying that we change the stereochemistry of a compound when it undergoes SN2 reaction. Said that if it's an R enantiomer, we will change to S. Very simple. We should keep that. Good. The next type of reactions we have to talk about are elimination reactions, right? Good. So elimination reaction will involve removing the halogen and then a hydrogen, so a dehydrohalogenation. Dehydrohalogenation. Good. So what happens is that we have two different mechanisms. Right, let me share a white screen and then explain the two different mechanisms. Once we are done explaining, we'll come and read the slides and then quickly would go on. So then let me share a white screen. Good. So the E1. Now in the E1, just like the SN1, we are forming a carbocation, right? Good. So we have a compound like C. Now there's Br here and there's H here, right? I won't focus on all the other parts of it. This is the most important part to me. So what happens is that the Br, which is a good leaving group, will go away on its own, right? So I'll have the C here. Now when it's going, it goes with the electrons there. So then I'll have a positive charge forming here because this carbon will lose the electron, right? Good. Then I'll have Br minus because it went with it. Good. Now the next thing will be that a strong base. Now the strong base we need here is usually an alkoxide. You realize that alcohols can act as weak acid, right? And then when the alcohol acts as weak acid, they form an ion called alkoxide, right? Now, because these are weak acid, its conjugate base is a very strong base. So if we need a very strong base, we go in for the alkoxides, right? The alkoxides. The alkoxides are very strong. So I'll use something like ethoxide. So ethoxide is CH2H5O minus, right? Now the ethoxide is a strong base, can take this hydrogen. It can take this hydrogen and then the bond will break onto this. This bond will break onto this. So what I'll have is C double bond C. And the double bond is coming because there's already a bond here, and then this bond is breaking onto this plus C2H5OH, this ethanol. So when this one takes the hydrogen, it will neutralize, it takes it as a proton, neutralize the negative charge here, and then it becomes ethanol, right? Good. So ethanol is part of the side products formed. Good. So that is that for that. Now this will be our final product, the alkene. This is the unsaturation we talked about when it comes to elimination reaction, right? Now, because the reaction involved the formation of a tertiary, of a carbocation, right? We say it is E1, and then as we mentioned in SN1, tertiary will be favored than primary, and then tertiary will also be favored than what? Secondary. Secondary will also be favored than primary, and then the least favored will be the metal, right? Good. Then the reason will still be the stability of the carbocation form, which I've already explained. Good. Now let's go to E2 reactions. So in E2 reaction, just as SN2, we don't expect any carbocation intermediate to form. So what happens is very simple. This hydrogen, this will be our halogen, right? So then what happens is that we will need a base. As the base is taking the hydrogen away, the bond is breaking onto this carbon, and then the S group is going away. So everything happened just in one step. So in one step, my strong base is taking the hydrogen away, right? Good. And then the bond of the hydrogen is now breaking onto this carbon because it's positive, right? The negative electrons are breaking onto the positive, and then this bond is going away because carbon is about to form a new bond, and carbon will not form 5 bonds, right? So I will have C double bond C as the main product, and then I'll have the X minus as side product, and then ROH as side product. That's after the base has taken the hydrogen. Very simple. So this is E2 reaction, right? Very simple. Very simple. So let's go back to the slide and then read through the notes we have been given. All right, so if you look at the reaction here, we have an alkoxide here, right? The alkoxide will, the whole reaction will proceed by removing hydrogen and then bromine. That's dehydrohallucination. From an alkene, you have an alcohol, and then you have your salt, right? Your salt. Good. Now the salt is formed because the base came in a salt form. So instead of having the Br minus, we have the K attached to the Br minus. Good. The same thing here, right? Hydrogen goes away, chlorine goes away. There will be unsaturation formed here. And then we have our alkoxide. That's the condition we need. So they have explained the E1 mechanism here forms a carbocation intermediate. I've said that already. We can read to the note. I'm sure we'll be able to follow. So this one goes away, forms carbocation. The base will remove the hydrogen here. The bond will break onto this one, right, and form our alkene for us. Very simple. E2 mechanism, everything happens in just one step. Base stays the hydrogen, the bonds break onto this carbon, the halogen goes away. Very simple. Good. Now, if we are given questions to draw the product of elimination reaction from dehydrohalogenation, very simple. These are the steps we are supposed to follow. We are supposed to find the alpha carbon. The alpha carbon will be the carbon bearing the halogen, and then we identify the beta carbon. The beta carbons will be all the carbons around the alpha carbon, and then we remove the halogen from the alpha carbon, and then remove the hydrogen from any of the beta carbons at each step, and then form new products, right? Good. Now, when we remove that, the two of them will form an unsaturation or a pi bond. Very simple, very simple. And then the condition we need for the elimination is a base. Now, the base we need should be a strong base, and then usually we prefer the alkoxides. So, example of alkoxide, this is an alkoxide, that's sodium ethoxide. This is sodium ethoxide, potassium tetbutoxide. Good. So now we've said that the E1 is similar to E2. Sorry, the E1 is similar to the SN1. The E2 is similar to the SN2. So in reaction, how the reagent decide whether to follow E1 or SN1, right? Now, that is what this slide tries to explain. So we are saying that there are two mechanisms of elimination, E2, E1, just as there are two mechanisms for substitution, SN1, SN2, right? Good. So SN1, SN2. Good. Now we are comparing E1 and SN1. We are saying that both of them are unimolecular. I mean, the determinant step is on just one of the species. Now, E1 is favored by the same factors as SN1. The factors are a polar protic solvent, the ability to form a stable carbocation, highly branched carbon chain, right, that's tertiary, good leaving group, and then the absence of good nucleophile. So these are factors roughly mentioned for E1 and then SN1. But then we are saying both, because both mechanisms occur under similar conditions, the two are competitive, and directing a reaction towards either E1 or SN1 alone is difficult. Now, what can help us decide is that if we want to follow E1, then we have to increase the temperature, because higher temperature favors E1 pathway. Very simple. Good. Now we are comparing E2 and SN2. So we are saying that a stronger base will favor E2. So if I use sodium hydroxide and then another person use ethoxide, sodium ethoxide, right? The one who used sodium ethoxide, good, is using a stronger base, and then that person might have E2 forming. So I'll form unsaturation instead of substitution, right? Because the butoxide is stronger than the hydroxide, sodium hydroxide, right? Good. So we are saying that a stronger base favors E2 over SN2, since strong base will pull off the beta hydrogen before it reaches the alpha carbon. So we are saying that if you have a very strong base, what happens is that now, in the base can either, that the base is coming as a nucleophile, so it can either come and substitute itself in S reaction, or it can remove the hydrogen in E reaction. If it's very strong, it will first of all remove this proton, right, before it even gets here. Now, because it will remove the proton when it's very strong, right, it will follow the elimination, right? But then if it's weak, it cannot really remove this proton, so it will go and substitute itself here because it's a nucleophile and this is positively charged, right? And then that will follow the substitution. So use a very strong base if you want to follow E2, and you use a very a moderately strong or a weak base if you want to follow what SN2. Very simple. Very simple. We are also saying that a bulky base nucleophile will undergo E2 easily than SN2. Now, SN is a substitution reaction. It means you are bringing something to be attached to a carbon which is already in a bond, right? We are forming a pentacoordinate intermediate. Now, if the nucleophile coming in, if the base is very big, it cannot be substituted to form the pentacoordinate intermediate. And so if you want to follow E2, one thing that you can do is that you can bring a very bulky base or a very bulky nucleophile as the base, right? Once it's bulky, it cannot undergo SN2 because it cannot be attached to the carbon that already has the 4 bonds to form the pentacoordinate intermediate. And once that pentacoordinate intermediate is not formed, we cannot go through the SN2 mechanism. Very simple, right? So this is a summary of whatever we've talked about here. We are saying that when trying to decide whether it's substitution or elimination, use the following to decide the structure of the substrate. Now, if it's primary, then we are thinking of either SN or SN2 or E2, right? Now, if it's tertiary, SN2 cannot occur, right? Because of steric hindrance, right? Because of steric hindrance. Now, the nature of nucleophile or base. Now, if it's strong and bulky, then we are thinking of elimination. If it's small and then strong, we are thinking of what? Substitution. Then the solvent we are using. Now, if the solvent is polar and protic, if it's a protic and polar solvent, a protic and polar solvent would have oxygen directly bonded to hydrogen or hydrogen bonded to either of oxygen, nitrogen, and fluorine. Oxygen, nitrogen, and fluorine are electronegative atoms, right? Now, if we have any solvent with hydrogen bonded to any of these compounds, we call the compound a polar protic solvent, right? And we are saying that polar protic solvent favor SN1 and E1 reactions. Example of polar protic solvent is water, alcohol, formic acid, ammonia, acetic acid, and then HF. This is also a solvent, right? Good. Then we have SN2 reaction require polar aprotic solvent. So some solvents are polar, right? They are polar, but then this is acetone. Acetone is polar, but then it has no hydrogen directly attached to any of these atoms, right? And so for SN2, we require this solvent, polar aprotic. So example of polar aprotic is acetone. We have crown ethers. We have dimethyl sulfoxide. We have acetonitril. So to mention but few, there are many, right? Good. Now, other organohalogen compounds. So we have acyl halide. This is the acyl group. This is the acyl group R. Or half bond. So this is the acyl group. When the acyl group is bonded to a halogen, we call it acyl halide. Now, we have a vinyl halide. This means if we have a vinyl group bonded to a halogen, is a vinyl halide or vinylic halide. Then this benzene group is called an aryl group. If it's bonded to an halogen, it's called aryl halide. Right? Now we have to read this slide. It's telling us importance of why we are learning topic like this, because the starting material, that is vinyl chloride, can be used to make PVC, very important polymer, right? In so many plastics, very important polymer. So we can just read it. We should read it. Then DDT is also a compound gotten from alkyl halides. You realize that the final product DDT has a lot of chlorine bonded to hydrocarbon chains, right? And that is alkyl halide. Good. 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 So that is it. This is DDT. This is how it's formed, right? Good. So now chloramphenicol, a broad spectrum bacteriostatic antibiotic, right? Now this is the formation. I'm not sure Dr. Bube will worry us with the formation of chloramphenicol, but then we should know the importance or compounds on the market that are alkyl halide. She can ask. So she can ask you And then the answer will be chloramphenicol, PVC, and then DDT, right? Good. Now other products, germicides, and then disinfectants. So yeah. Good. Now we have refrigerants like chlorofluorocarbons, which are not in use again because of their depletion on the ozone layer, right? Good. Now these are the new ones that we use. Now they are safer for the ozone layer. So an exercise for us to try, we are supposed to classify the following organic halide into primary, secondary, tertiary, alkyl, aryl. So this one is the carbon here is bonded to 3 other carbons. This is tertiary. This is an alkyl, right? Alkyl. This one here, this carbon is bonded to 2 other carbons. So this is a secondary. This is an aryl because of the benzene group here. Aryl. Now this is primary because this carbon is bonded to one other carbon. Primary. Now we are supposed to arrange this in order of increasing. So this is a primary carbocation because it's bonded, the carbon here is bonded to just one other carbon. It's primary. This is a tertiary because the carbon here is bonded to 1, 2, 3 other carbons, right? So tertiary. And this is secondary because the carbon here is bonded to 2 other carbons, so secondary. And then generally, in terms of increasing, is primary, secondary, tertiary. Tertiary is the most stable. So that is that for that. Now we are supposed to explain SN1, SN2. Let's read through this. One thing I know about Dr. Abna Brobe is that the questions in the slide are possible examination questions, so we should read through this. I'm sure we will understand this one if we have watched the video. Good. So we should go through this example. Now, this is the last thing we would learn for today, and then we'll end the whole presentation. As I said, this is an initiative by Samuel Tampanga Wepia, an aspirant for the College of Health president. Now, if you think this is a good initiative and then it would help you in the coming years, I'm sure if most of you had materials like this, chemistry would have been easy as it should be, right? So if you think this is a good initiative, then you kindly hop on board so that we can make it possible. This is among the numerous policies that Samuel Tampanga Wepia is planning on bringing on board. Good, so let's explain this slide. As I said, this is an academic material, so you should use it irrespective of your political affiliation. Now, these are substituents, right? Good. Sometimes we hear things like sec, butyl, tet, isonew. So we are using the slides to explain them. So if I talk about methyl, this is the normal methyl group, and there's nothing like anything. So I can't say sec methyl, tet methyl, isomethyl. So the empty space so that there's nothing of this that can be applied to methyl, right? You see, this is a normal ethyl group. None of this can be applied. This is a normal propyl group. Now there's another thing like isopropyl. Isopropyl. Right? Now, if I see iso, it means there is a split end on the second to last carbon. So assuming I have, let's say, 5 carbons, right? Now, this is where it attached to the parent chain. This is a substituent. And there's a split on the second to last. So this is the last carbon. This is the second to last carbon. If there's a split here, no matter the chain, and once there's a split on the second to last, then it becomes a new, right? Good. Sorry, it's not irrespective of the chain. If there's one split, so if there's a single split here, then it's a new, right? Good. So if I talk about new propyl, it's iso. It is iso. It is iso, right? So if there's a split, it is iso. It's not new. Good. So if I talk about isopropyl, propyl has 3 carbons, right? So 1, 2, 3. Now I cannot draw the 3 here. The last one should be a split. So this is how I'll draw it. And this will be attached to the parent chain. Said that if this is the last carbon, the last but one is this one, and there's a split. So this is isopropyl, right? Good. Now, if I talk about sec, we are seeing that sec, the first carbon on the complex is connected to another carbon atom. So sec is secondary, right? Sec is secondary. So if this is the parent chain, right? And then this is attached. The first carbon here attached to other carbons. If it's attached to another carbon, that's if there's a split. If there's one split on this first carbon, which is attached to the parent chain, then we call it sec. So I can ask you to write sec-butyl. Sec-butyl. Sec-butyl would have the first carbon here, which is attached to the parent, right? The parent complex chain bonding to other alkyl group as here, but then it has one split. This carbon has two splits. Now, because the carbon has two splits, it is secondary, right? And then that is sec-butyl. Good. Now, the total number of carbons here should be 4 to show that it's butyl. Now, if I talk about tet, it means the carbon which is bonded to the parent, right, has 3 carbons attached to it. So tertiary, right? So that is what has happened here. This H shouldn't come, is a mistake, so you rectify it. This H shouldn't come, right? I don't know if you were taught in class, but this H shouldn't come. Good. So that's you realize that this carbon, which is bonded to the parent here, has 3 other carbons bonded to them. This is tet. So this is tet butyl. The total number of carbons should be 4 to show that it's butyl. This is the normal butyl. This sec butyl. This tet butyl. If I talk about isobutyl, it means the last but one carbon should have one split. Very simple, right? Then this is pentyl. Normal pentyl, 5 carbons, right? Then if I talk about sec pentyl, it means there should be a split on the first carbon, right? So one split on the first carbon that is attached to the parent. Now, if this split occurs on the last carbon here, last but one carbon, if the split occurs on the last but one carbon, then I'm talking about iso, right? I'm talking about iso. Now, if this first carbon has 2 groups, that is, it has 2 groups, so this group and this group is sec. Now, if it has 3 groups, this hydrogen shouldn't come. Yes, if it has 3 groups bonded to it, right? If you have 3 groups bonded to it, like we have here, then it's a tertiary, right? Good. Now, we are saying that if it's new, then there are 2 splits on the last but one. So this is the last carbon, this is the last but one carbon. If there's one split, it is iso. If there's 2 splits on the last but one carbon, then it is new. So this is new pentyl. The total number of carbon here should be 5 so that it shows it's pentyl. So you can try these ones. You can try for hexyl, right? You can try normal hexyl, sec hexyl, tet hexyl, isohexyl, and new. Let me even try it here, and that will be the last thing we'll do when I sign off. So yeah. So hexyl chain 1, so this 2, right? 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So this is hexyl, right? So this is hexyl. Now, if I want to draw sec hexyl, it means the first carbon here, I should have a branch on it, right? So what will happen is I'll have, this is the parent. So 1, 2, 3, 4, 5, right? And then I'll come and put the last carbon here. So this should be sec hexyl. Sec hexyl. Assuming I want to draw tet hexyl, it means this carbon should have 2 substitutions. So this is my parent. So I'll draw 4 carbons. That's 1, 2, 3, 4, right? Then 5 and 6. So the 2 carbons will be here. And this will be tet. This will be tet hexyl, right? Tet hexyl. Then if I'm supposed to draw isohexyl, this is my parent chain, right? Go to 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Good. Then the last but one should have one split, so 6. Then this will be isohexyl. And the last one will be new hexyl. So new hexyl says there should be 2 splits here. So my parent, 1, 2, 3, 4, right? And the last but one will have 2 splits. So then this will be new. This will be new hexyl. New hexyl. Good. So I would like to sign off here. My name is Samuel Tampanga Wepia, vying for HESA President next semester. If you have any question or clarification, when you see me, you can just ask me the chemistry question. I'll answer it. Or you can then see any member of my team, or you can also see any member of your academic board or the lecturer in question, Dr. Abna Broby. Thank you very much for your audience. And then enjoy the rest of your day. Bye.